Well, let us see a very specific example of dealing with the learning problems. We are not really going to solve the learning problem. Just want to show how the four elements in a practical example. I'd like to use a programming environment. So to make this example very specific, I would use Python. Well, as at the time being, 2020, this is the most popular programming language in data science. But as far as this example is concerned, it does not actually matter which kind of programming language you use. You can also use script-based tools. That does not change the nature of the problem. But I think Python will provide you a very clear example, and it provides you convenience in accessing and processing the data. So you are also saved any trouble to set up the local environment on your computer. I will use the environment provided by Google. If you want to follow me in this example, you just need to go to Colab, C-O-L-A-B, colab.research.google, and then it will guide you to create your notebook environment. By notebook, it is a front end of a web-based service, and at the back end, Google Cloud runs Python computational environment for us. I'll create a new notebook. Let us give it a proper name. Machine learning 001 maybe. Okay. Python provides you very convenient toolset to perform machine learning tasks. In this case, I will use the scikit-learn toolbox, but I do not want to use the tools in the scikit-learn. I just want to use the example dataset comes with scikit-learn. So I will import scikit-learn. This is just to check whether this library is ready. So if you click this icon, the notebook will start running. In the first time you run something in a notebook, it will initialize whatever allocate memory virtual machines for you. Okay, this library exists. Well, that is a very good preparation by Google. Actually, I would not use the entire scikit-learn. I just want to use a data set comes with this library. So I think I will change this into from scikit-learn. If you type and pause for a little while, it will suggest probable completions from the context of your programming. Well, I will use its data sets. From this module, put load arrays. You will be very familiar with this flower dataset by now. Let's run this. Good. See, now I'll create another code block, and I can keep my previous code block there for reference. And now we are running, executing new experimental codes from below. This, these numbers shows the order in which you have executed those code blocks. So you do not necessarily linearly run them from top to the bottom. You can go up and down to the experiment, which is really convenient. So let me call a database as load virus. This is a function. After calling this function, we will have an object called database. This looks like a data set, right? So look, in this object, we have different fields. This is a dictionary. In this dictionary, with a key data, the content, the value associated with this key is an array. Each row of the array contains 4 values imaginably that represent one sample of the flower. Well, there is a target array as well. You can understand this corresponds to the class IDs. Well, it is very considerate, also provide you the description of the meaning of those features, which just an alternative name for attributes as well as the targets. So now consider you are facing the task to build some function. To build a function in Python is as simple as this: a definition of an f. This is a function, so it is followed by a pair of parentheses. You return something. For now, you don't have anything to return, but this is a legitimate function. Now you have this function. So you are facing the task of building this function so that, presumably, you would like to have this predicted equals or to be assigned as a function x1, x2, x3, x4, and hopefully this prediction agrees with the corresponding y with this x1 to x4. So how to build such a function? In this very moment, something comes to your mind is, okay, I need to figure out the input of my function. Well, you have 4 variables as input, and you need to return some y. The job is to come up with some form of converting the values of x1 to x4 into y, right? And hopefully your returned y agrees with the y you have observed from the data. This is a hypothesis because in the learner's mind, we have hypothetical we need to assume some relationship between the attribute and the target, and later we will compare our assumption with the observation of the reality. To form usable assumptions, we need to limit our imagination to have some consolidated families of function we are considering here. For example, it could be as simple as this. If x1 is less than, for example, 3.2, we would like y to be 0. Otherwise, let y to be 1. Obviously, this won't be a very useful hypothesis. For example, it ignored the possibility of y is Virginica at all, but it's viable. It's a viable hypothesis. If you give it a legitimate legal input, it will return you a legal output, although the quality is of question. So this is one bit of the hypothesis. Let's call it hypothesis 1. Okay, then let's continue our exploration. Let's also build a hypothesis 2. Okay, now we start having a family of hypotheses. Although now the family is very limited. We have only 2 members in the family, but we have multiple members, and this makes a family. Say, in the second hypothesis, let's say, no, maybe I want it to be flipped, to have flipped prediction against the first hypothesis. Well, these are 2 different hypotheses. Then how about let us limit our simplify the problem of distinguishing the first class, the Setosa, from versicolor. So let's forget about Virginica for a moment. Now let's perform some basic learning. Okay. Say if we have x1, x2, x3, x4, we let these 4 values to be our data. To be our first data sample. Remind you, Python indexes arrays starting from index 0. So index 0 represents the first sample in an array. And because this sample in the array is a row of a 2-dimensional array that contains 4 values, you are allowed to assign 4 values to unzip them into 4 separate variables. And now let us compare the prediction of our 2 hypotheses. Prediction 1 will be hypothesis 1, x2, x3, x4, and prediction 2 to be f2, x2, x3, x4. Now let's examine them. The predictions are prediction 1 and prediction 2. When you put an f in front of a string, then it will interpret anything in curly braces within the string as variables. So first, let's execute this. You have to define those functions before you use it. So look, we have different predictions according to these 2 hypotheses. And the next reasonable step is, how about let us compare these 2 hypotheses. So this very simple conceptual learning procedure will finally give us a choice, although within this very limited family. I don't want to further complicate the problem. So I know that for the first 100 samples in Iris dataset, they are the flowers belong to the first two classes. And let us for now ignore the very wise suggestion of splitting the data. This is wrong. We shouldn't do this. But just for now, let us consider the procedure of comparing hypothesis to data and not worrying about evaluate what we have learned later. Okay, so we forgo the split step and compare the hypothesis in the first 100 samples. Okay, so correct number 0, that to be 0, and correct number 1, that to be 0 as well. This accumulates the correct predictions of the two hypotheses. Then we do a for loop for all x and y in zip means let us put two arrays together, and in the for loop, each of the loop, because we have two loop variables, we will take one from the first collection in the loop and take the second to be y. If you do not understand this part, don't worry. You can do a dummy for, which means you do nothing, just break immediately after you entering the for loop, and then you can have a look of what is x and what is y. So let's just do this. Yes, these are the observation and the target value of one data sample. And you can imagine if you loop through all the data sets, this x and y variable will go through all the 100 samples. So to specify that we do not want to go through all 150, but only the first 100 samples, we specify it using this. Okay, fine. Now let's copy it over here. We will distribute the values in x into 4 variables and use these 4 variables to call the two hypotheses. Okay, so this part we can just reuse them here. And then that's the time to increase the correctly classified samples of the two hypotheses. Okay, so track 1 equals y. Then, okay, I admit the variable name is not so great. So let's keep this consistent. Call them number 1 and number 2 rather than number 0 and number 1. Okay. Let this to here. Increase by 1. And correspondingly, if you encounter errors when following this tutorial, the first thing you can do is copy your error message to Google, and probably you won't be the first person encounter the error. Well, there are also some cautions you can take. For example, Python is very particular about the cosmetic aspect of your programming. you're supposed to keep a consistent indent of your code with respect to the logic levels of those code blocks. You are not supposed to use 4 spaces here and 3 here. Then this will confuse the language about the logic relationship between those statements. Okay, anyway. Then let's print first hypothesis f1 has this number of has been correct. Okay, sorry. Hypo f1 performance is this. Hypo O f2 number is this. Okay. Okay, fine. Let's run this. Wow. Interestingly, this seems to be very unhelpful evaluation. We have exactly same number of correct and incorrect classification of these two hypotheses, which means they both perform very badly. Let's check if we can do something a little bit more interesting. See, let's call it 6.2 rather than 3.2. Okay. Okay, now it seems that the hypothesis F1 performs a little bit better than the hypothesis of F2. So obviously, I would not like to call this is a great learning program, but this is gives some idea of the elements in the machine learning procedure. So let's come back to the slides. The 4 elements, when you mathematically denote them, they normally like this. For the data, these are the data samples. There are 2 parts in the data sample, the observed attributes and the target value. I need to remind you this is normally the source of randomization. When you have designed your learning system, it is quite often that all the other parts are fixed, and but you still face uncertainty in the performance and in how the learned model will work in practice. And this stochasticity is generally caused by the fact that data samples are random samples from an unknown distribution. And then it is very important to set up a hypothesis and a family of hypotheses. As we have seen in our very straightforward sample minimalist example, we have 2 hypotheses. We call this a family, and we will learn in this semester in this subject a couple of useful families. Well, we need to define the criterion, and the criterion is actually one important factor to define what is the task. For some kind of task, such as if you want to predict the share price, this part is pretty clear how you can do that. On the other hand, sometimes the criterion is not so obvious. For example, if you are doing a classification task, but when the classification is correct, easy, the loss or the cost will be zero. But when it makes errors, it depends on the context of the scenario, how those errors cost. For example, if you want to detect inappropriate behaviors of supermarket customers, in this case, if you misclassify who is a proper customer, who is a respectful customer, as one that is perform shoplifting, you will face a very angry customer and the loss is significant. On the other hand, if you misclassify some real thief as a normal behaving customer, you may lose some money, but normally the sum of money won't be that great. So you probably want to design the same system on the to err on the safe side. On the other hand, if you want to identify suspicious attempt of entering a nuclear plant, and the scenario totally changes the cost of two different types of wrong classification. So sometimes the loss is very much depending and defining the task. We will discuss this later in the semester with very rich very rich choices of different laws and very interesting machine learning tasks. And of course, there is a learning algorithm. We will put much focus on this bit in the semester. And finally, we can deliver the learned model.